Before I start, I want to say that I'm very happy here, and I want to start with a interesting story. The way that I know Dr. Georgia Garkos is we attended a conference in Egypt, and as part of that conference, we had a lot of government official attending the conference, and then they divided us into working group to come up with solutions for possible pathways for Egypt's water resource problems. And then there were a couple of different working groups. Most of them didn't have much to offer. And then our group, we were lucky to have Dr. Georgia Garkos to get up. He started talking. By the end of it, he basically offered solution for almost every part of it, and became obvious that he knew more about Egypt's water resource problem than most of the government officials. And then I knew that we are in the right hands. So with that, I'm going to get it started to basically tell you about the work that we have been doing. And it's a work that is now close to a lot of the stories that we hear. These images are becoming common issues. Now we have flood in this massive scale. One of the things that I want to discuss is, what's going on, and then why we're seeing it at this scale and why this is happening. Well, we are now seeing these because we have a lot of vulnerable communities. Over time, we have built in the wrong places for the past 300-400 years. We wanted to be close to the water. As great that is, a lot of risks are associated with it. And over time, we have neglected a lot of the maintenance issues, plus the fact that the climate is shifting, and we have not really, developed solutions for it. And a lot of these infrastructures that we have, they're at a place that they're vulnerable. You may have noticed and heard that, okay, so some of these effects are going to become worse than before. One of them, you have rising seas. What does that do? Well, that one is going to push water further. One of the problems that we have in the US, we have a shallow continental shelf, meaning that every inch of rise means more momentum for that water that comes in. But in other places in Europe, so you have a steep shelf like that provides some buffer, not here. Over the years, I've been doing this research for many, many years. This image I created in 2005-06. This was after Sandy came in. We started looking some of these stuff, added then what happened during Sandy. The projection that we had at a time, I knew that if a Category 1 storm hits New York City, city is going to be very vulnerable. And at the time, I was talking about 3-4 feet of water. Most people were telling me that, where are you going to get all that water from? And then Hurricane Sandy happened. And then by the time that Sandy hit New York City, it was a superstorm. It wasn't even a Category 1 hurricane. Got a fancy name to help them declare emergency. But the wind speed at the time when it hit New York City was around 50 miles per hour. That is 24 miles per hour of wind speed, short of it being a Category 1. But now, look at the impact. During Sandy specifically, let me just go to the inundation map of Sandy itself. 31 subway entrances were flooded, 88 miles of railroad, 80 miles of highways, and major areas of the streets were flooded. Major part of the city were out of any kind of power for a couple of months. Now, look at the impact of Sandy in compared to other categories of hurricane. Namely, look at Sandy, wind speed of 50 miles per hour, and a projection for the Category 1. So how is it a storm with a significantly less power leaves a damage behind that is more than a Category 1 hurricane? Anyone? Anyone has a thought? Why could that be? You told me this guy is only 150 pounds. All of a sudden, I'm all bruised up fighting him. What happened? Any answers to that? Why a storm that is significantly weaker than a Category 1 based on the projection leaves a damage behind more than that Category 1?
The city itself is vulnerable.
City itself is vulnerable. There are a lot of, other issues. Every year, American Society of Civil Engineers, that all civil engineers were kind of part of it, puts out these report cards. And then you see C's and D's for your bridges, for your roadways, for your rails, for your water resources systems. And you think this is okay. You think that, I got these in college and I turned out to be fine. But in reality, it has major implications. Major implications. So we have a holistic view of that entire system that could be severely vulnerable. One of the things that I have done, I basically put this together to give you a sense. One of those infrastructure that is very vulnerable is our water treatment facilities, wastewater treatment facilities in New York City. 13 out of the 14 wastewater treatment facilities were damaged during Sandy. You're talking about hundreds of millions of dollars of damage. And often we look at these events in a vacuum. All right, we have 100-year rains coming. All right, we have a Category 3 storm is coming. What if a Category 3 comes after 3 days of rain during a high tide? And the entire city will go underwater. If you have been following the news, I'm specifically talking about Houston. Houston got 48 inches of rain in 3 days. You know how much Houston gets in 1 year on average? Around 40. So you got 8 inches more than what you get in a year. The entire city went underwater. Do you think that was a new incident that Texans didn't know about it? The whole reason that Houston was built was because the city of Galveston, Texas, once a thriving city, port city, got hammered during 1942 hurricane. And they decided, you know what, this is not a good place to live. Let's move to Houston. But guess what? We are going to do the same thing that we have been doing in Galveston here. Resultant, same. Same practices that failed over there will go fail over, in this place as well. So we can't look at these events in a vacuum. We can't look at just one of them. These are compound effects. These are cascading effects. That's why I have developed this concept of total water level. Don't look at that just one level. Just don't look at just one scenario. Just look at the whole system. What if you have a couple of days of rain and then you have a major storm that happens during a high tide? That is happened to be because of the climate change. You already have higher water levels. In a lot of coastal cities, now we have something called nuisance flooding or sunny day flooding. What causes that? There's no rain outside, there is nothing, and then you see flooding comes right in. You have it in Miami, you have in coastal New Jersey, Carolinas, all over the country. Why is that? That is precisely that effect of that sea level rise over time. The water now gets pushed in. When I was working on these, there's the study that I'm going to talk about. It was funded by New Jersey Department of Community Affairs to get a sense of what happens to these communities. I only did my projections for up to Category 4. They were really on me to go ahead and do the projection for Category 5 as the worst case scenario. I was keep saying no, and I was trying to explain it to different people. They weren't getting it. One time I got them into the room and said that you have to understand some of the fundamentals behind it. Category 5 will never happen in New Jersey. We are all the way up north. We are 40 degrees north in latitude. Any storm that comes here, storms happen between 0 to 25 degrees north, and eventually they will come up, they hit the westerlies, they get pushed back in the ocean, or they come up there, they hit the jet stream, they're pushed back in the ocean. If a storm of a Category 5 comes up to this area, I am not going to be in lab calculating. I'll be in church on my knees praying at that time. Because that means the whole system now got destroyed in a way that none of the fundamentals that we have, global wind patterns, jet stream, none of that, works anymore. That means the water is so warm that hot water got all the way up to the northern part of that system. As an evidence for it, if you have ever read about Hurricane Katrina, the night of August 12th, I believe, it was only a Category 1 storm with a 74, 75 miles per hour wind speed, right outside of the Gulf of Mexico. That night, I was following it. I went to sleep, woke up in the morning, checked out, was a Category 5. Got into the Gulf of Mexico, became a Category 5. Where did all that fuel came from? From the sea surface temperature the main driver of that maximum potential intensity that was available in Gulf of Mexico. Outside, water temperature was around 20s. Got into the Gulf of Mexico, temperature dropped around 28 degrees, 29 degrees Celsius. Was enough energy available to shoot a category 1 to category 5. Went from a 75 miles per hour wind power to over 200 plus. And if you think that is not powerful, you haven't seen category 5. And that destruction because of it. So it is important to understand these nuances. So at a time, I explained to the government officials that if I understand correctly, you're asking for a category 5 because you want to know your worst case scenario. But you know what is your worst case scenario that is reasonable? Because responsible modeling is important, not putting out wrong information. Your worst case scenario is a category 1 with a couple of days of rain during high tide with all these neglected maintenance issues. And I practically, taught them over there that you just need a 3-finger flood forecast model. And I was like, what is it, Dr. Nazari? I was like, you know what? If you have a 15 miles per hour wind speed, northwest direction, during high tide, I will show you specifically what the streets in Ventnor, Market, Atlantic City, Ocean City will get flooded. So that means something has to be done. So the meaning of this total water level is to accommodate those cascading events. The other thing is, as much as we think that the stuff that we do in the lab, the research that you do is advanced, none of this gets to the community level, believe it or not. So when I was doing this research at a coastal resiliency lab, over 35 mayors of different small towns will come to my lab. Every time they would come with a FEMA map from 30 years ago. Oh, look, this area is, we are in A zone, and V zone, and VE zone, and all that. Well, one thing is, those maps are 1, outdated, 2, admittedly, FEMA is a Federal Emergency Management Administration dealing with a national scale catastrophes. They're not made for small towns. They're not made for city planning. And now they came up with Risk 2.0. A lot of communities are upset about it and all that because they don't reflect what it is. So none of these high-level stuff gets to it. I was like, we have better stuff. But the problem is, because of the fact that a lot of planning is done based on it, it brings that false sense of being safe in this case. What I'm showing you here is a map from Mexico Beach, Florida. This is during Hurricane Michael. The map shows you that this front area is in a V zone, the other one is the A zone and the X zone. If you're familiar with FEMA maps, A zone is a zone of a 100-year flood. V zone is 100-year flood plus wave. And what is that E? That the notion of E added, that means this is part of NFIP and base flood elevation, BFE, and then design flood elevation, DFE are known. That means we know those. So that's why you see that E's. What is that X zone? Unshaded. That is an area outside of the 500-year flood. So you look at this map and you say that, my house is here and I should be fine. Okay, so now I'm going to show you Hurricane Michael to this exact area that was in X zone. X zone is completely wiped out. Who's responsible for it? By the way, in A and V zone, you are required to have a flood insurance. In X zone, you're not. But your flood insurance premiums are a fraction of what it is in A zone. But because you have this false sense of security, you're not going to go buy flood insurance. And then you get destroyed. This one guy, they interviewed with him, he said, I spent a couple of $1,000 on resilience measures, and then my house is still standing. One of the issues that now you hear in Florida that their insurance premiums tripled and quadrupled, this is crisis going on, is exactly this. As much as we think that we are in charge of some of these scenarios, we are not. In the United States, most of us are not the owners of our home. Number one owner is the bank. Number two is the insurance company that is actually securing that mortgage. And number three is us standing with our 5%. The bank is not going to take those kind of risks anymore. And that's why all the insurance premiums and all that significantly went up. So when I was working on this, I was looking at what can we do to work on resilience measures. I said, okay, so what is the definition of resiliency? What is it that we're trying to do? Well, the resiliency is the ability of a system to prepare for, withstand, recover from, and adapt to an external shock. And it basically comes from a lot of components of the communities. In order to do this, this isn't just the water resources problem. This is a whole decision-making problem for an entire system that is connected. In order to understand this, you have to go back with some of the fundamentals of the functionality. So this is the map of functionality over time. This is the chart that you see. Functionality is as 100% up here, right? This is that straight line. So this is me walking down a path that is straight. All of a sudden, there is a pothole and I fall, right? So my functionality here drops. And then eventually I dust myself up and I start basically getting back to normal and start walking again. Well, that issue is a lot more delicate than you can think of if you bring it down to the system. Because the issue is, what is the time of that recovery? What is the time of that recovery? And I'll come back to it. So now, looking more at flood is important to understand that entire system. Looking at flood damage, what causes, all that other information like the construction type, height of the building, age of the building, the elevation of the basement, and all that comes in. And when you put it together, you study the system, you realize that flood is significantly understudied. Significantly understudied. Because disaster for us before was only earthquake. Flood is now, after we paved everything, now we're seeing flood and flash flood that in a matter of 1 hour, you see flood before, 20 hours later, you will see that water accumulation. Now, time of concentration is less than 1 hour. You call it flash flood. So here, if you look at it and you put all these buildings together, you see that earthquake used to target larger structures without touching small structures much. Flood is different. Flood targets all your smaller 1-2-story buildings, or we call them earthen structures. Practically doesn't touch much of those large structures. But the problem is 99% of your system is made out of those smaller structures. So that's why it is significantly more devastating, even in a smaller scale. Because now, even a category, if it is earthquake of a 6.5 doesn't have that much destruction because buildings are ready for it. But even a smaller flood causes more significant issues. And the other thing is, the other area that has not been studied is the interaction of the fluid and solid system. The impact of the water with the momentum that it has on a structure. Did you know that just a 1 foot standing water can bring down an entire wall? So now imagine that water is moving. That water is moving. That same 1 foot of water that is moving at a higher speed can carry a car. So if you've been here in this class, next time you see there's a flood going on, there's 1 foot of water is just moving, don't decide to drive through it. It will carry your car. That's the momentum that you have. So understanding these will take some complexity and it has to be done. So at a time I wanted to do it for the state at 3 scale: macro, the large scale, meso, and also micro scale. Micro scale becomes very important because unless you understand risk right around your own properties, it won't register as much. Listen, I'm in this business. They tell me 6 inches of rain. I think that the gutter system, the drainage system should be able to take care of it. But that's not the case unless you see it in action. So that part, micro, becomes very important. But when you go into that direction, it becomes immensely complex. In order to do this, we had to go collect terabytes and terabytes of data. From the hydrodynamic side to the topography, to the structural data, to the population data, bridges, transportation, infrastructure, because my goal was to develop a decision-making framework for the entire system. Something that the mayor, the governor can look at it and make decisions for that system. Or if that is a small community, they could look at it and see where the vulnerable areas are. You would think that this is almost impossible if a company wants to do it, because this takes so much time. But we are at the university and we are at the luxury of having available graduate students that they could do all of that. So we were able to do this, collect all that data, and we were able to now translate data from those events to what happens to right around our waterway, from the time that a storm leaves and eventually comes and impacts my community at a smaller area, at a very high resolution, that now I can extract the vortices that I need to do flood modeling. Because what I need, not only just the extent that you see, but also now I need the momentum, plus I need the depth. So I need X, Y, plus the depth. That's why we call it a 2D. We don't call it 3D, because then if that is real 3D, your base, that third dimension needs to move with it, which is not the case here. With that, we also developed a new equation for flood damage analysis on the structure. So flood damage failure was basically developed. We don't have equations for flood like that. That's why we had to develop. For earthquake, all of that is developed. For this one, we had to develop, based on that information, we were able to calculate flood damage on every single structures that was out there. So this data, that large level data, was translated now to damage. Next was to basically understand if this could become a restorative curve. Something, again, doesn't exist for flood. For earthquake, you have these curves, they're ready to go. For, when it comes to flood events, we don't have. In order to develop that restorative curve, there were a couple of components. One of them was we were trying to also, from damage analysis and from that depth, to go to the meaning of resiliency. Because we had developed a damage index, now I wanted to develop a resilience index. With resilience comes the component of the time of recovery. So I was thinking for a long time that what would be the time of recovery? So initially I thought the time of recovery would be equal to the time of construction, right? For a single family, 6 months. But you go around after major hurricanes, let's say Katrina many years ago, Sandy many years ago. All these houses that are still dilapidated. You're like, okay, time of recovery is not equal to time of construction. Time of recovery is equal to time of construction if the money is ready in the bank and the community has enough resources to rebuild that property. Enough plumbers and contractors and all the other ones. And if that money is not available, next layer, if FEMA is going to pay for that property, if that government money is available, if not, is that the charity money is available, and so on. So that time of recovery becomes significantly elongated based on the community resources. So that became one of the major components to go in to be able for us to develop that time of recovery. So now, for the first time, we have restorative curves for storms. And next was now to develop that comprehensive system. So our comprehensive model was to basically have data on the hydrodynamic component of it, be able to calculate flood damage, flood depth, momentum, and all that, bring it into structural resilience. So this was that decision-making framework, looking at all these individual part of the system. By the way, as a part of it, we also calculated 2 more things. One of them being damage to the bridges, basically bridge failure index, which was a painful process. And the other one was a scour, basically around structures, because there are other ways of failure that is not just accounted to the force. It could be just the wash of the foundation. There are other models that I don't get a chance to really go in depth, but this became this whole process. And I will show you the result of it. There are a couple of more pieces that we're working on it. One of the other students, my PhD student Mujongo, is now working on bringing in AI, and he has developed the first round of it to automate this system based on AI to calculate the damage as an independent of this model. Basically, this is now a model based on equations. Basically, this is not a probabilistic model. This is imperialistic. Basically, we have equations that go into it. So now I want to bring AI to basically teach AI to follow this and do it for a significantly larger scale. And the other one, the other student, the other postdoc that is working, on here, Ali Reza, is working on the financial model of it to see that, okay, what would be the dollar amount as the dollar amount is changing, plus also calculate what would be the projected premiums for some of these houses to be insured. Then I thought that these are great, these are complex, but we will understand it. Civil engineers, we can talk about this stuff, it's great. But I was like, you know what? At the end of the day, this information has to reach out to public. Otherwise, it's just gonna sit on a shelf. And I thought that unless my mom can understand this information is not useful. I was like, you know what? All that fancy, equations, I'm gonna turn them into colors. So if the damage is less than 5% is green, 5 to 25% yellow, 25 to 50, it becomes orange, and if anything more than 50% for us becomes total failure is red. Using that, I color coded every single house in the system, every single house. Every time that I show this image, I get a chill myself. Because these are real houses, real communities, real people that being modeled do not know and have the information necessary and then decide randomly what to do in the case of a storm. When I showed this image to the mayor of this town, he almost fell off the chair. He said, Dr. Nazari, what are you trying to do with this? I was like, this is going to be the information for you to do the next round of the codes for the design and construction. This is going to be the information for you to have your police department, your first responders to know where they're going. This is information that you need to know that when you need to start evacuating. Chief of the police was there. So actually, if you have this, we could go door to door and especially mobilize the ones that are in red areas. But also understand, most of us in this country and even around the world, we are making our most expensive investment of our life completely blindly, not knowing any of these. So this, what you're seeing, is also the foundation of my startup, basically developing these information to make it available to homeowners before they purchase it. They could actually get this. So if you guys have bought a used car, you go and look for it on Carfax, right? So we're developing house facts. So everything you need to know about a house before you buy it, in terms of all that, right? It becomes very useful because then you have a sense of what can you expect. In terms of flood, and we're looking at other natural disasters as well. So these kind of information will basically find a way, in there. Yes, we are 10 years before ahead of the market, but I believe in a matter of a couple of years, eventually, this information will become available, whether we want it or not. Technology is moving that way. So as I said, there are a couple of other things that we have developed. One of them is a scanner for structures. The other one was bridge resilience. These are mostly custom-made products. If we have a specific, clientele that is asking for it, they want to do capital improvement, and they have access to that kind of fund. Can you give me a sense of time?
You're good.
Okay, just want to make sure because I don't have
Two,
it.
two, we are fine.
All right. Okay, perfect.
But let's try to finish 1:30, 1:40,
Okay, yeah, no, I'll try to. What time is now?
1:10.
Oh, 1:10. Oh, okay.
You're fine.
I was supposed to finish around 1:10, but that's,
Take your time.
okay, as long as that's fine.
Yes.
All right, so next was, now I have all this good stuff, but the other thing is, if you are looking at some of the new requests for proposals that are coming from the government, the issue is also the fact about equity. So who's going to be impacted, right? Because the impact is not uniform. So it becomes vulnerability. Who is vulnerable? When I was looking at vulnerability assessment and vulnerability indices, they were mostly developed by social scientists. So it was mostly about, their age and their education and things like that. They're, were they able to speak English, receive the information or not. But to me, that wasn't comprehensive enough, because what if you are elderly and you're sick and all the other ones, but you live in a very solid structure, a way that's not gonna be impacted? Do we need to really mobilize you? Now put you in a car and move you out of the area? Is that necessary? So that component was missing. So I developed our own vulnerability index to basically bring in all those population information plus the built environment and flood factors. This is now a comprehensive vulnerability assessment, now giving us a sense that who are truly vulnerable. Because the ones that are by the beach, maybe they're going to get damaged, but they have the resources that they can quickly move out. Because those are a couple of $1 million of properties, so by nature, they have the resources to do well. So naturally, if you are the city manager, you're the mayor, and you have only 20 trucks that you have to send out, where do you send them? So this decision making is to know where to allocate your resources. All of a sudden, the storm hits, you get hundreds of calls. Which one you have to take? Some people are genuinely scared, like, oh, the water is really moving fast. Like, okay, thanks for letting us know. But are you in any danger? No, I just wanted to let you know. Okay. But you have all the other ones that they could be really in danger. So having a system like this on top of your calls, then you're significantly more targeted. And if you look at some of the recent events, the ones that are in the decision-making chair, they don't have the tools necessary to do it. And you go down to the lower level, most of the towns don't even have a city engineer to even open a map or update the map. And maybe there's one engineer in 4 or 5 towns. You're talking about significantly more limited resources. I have a paper in publications about, can a small town America survive climate change? Because at the end of the day, Atlanta, New York City, Miami will survive because there's enough taxpayers, enough money to, even if necessary, to put it on a jack and move it up. But what about the small towns? They don't have the resources. And that's going to be the case not only here, but around the world. So if that information, that kind of information is out there, most people will decide otherwise in the case of next event to just stay home. In addition to this, bless you, we wanted to make sure this is comprehensive. Next piece of that was evacuation, because we had this mass warning system. You know, when the storm is coming, you know, let's go and all that, and all of a sudden, people get on the road and they're stuck. So having that information, using the same colors as a Google map based on traffic flow, overlaying that high resolution flood with the road information, you will see that, okay, what areas, what roads are going to be open, until when, and when is a safe time to come back. To my surprise, for these areas that I was looking at, the roads that they were designated for evacuation would get flooded first round, 8 hours before the actual storm that got there. So now imagine someone decides to wait until the last minute. How are you going to evacuate them? What would be the recommendation for them? So along with this one is a mobile app that is being developed that is basically going to be used during those, you know, emergency evacuation scenarios, and that's going to be the use for it. So with this, you have this comprehensive view of that whole system. But before I do that, I wanted to show you this. With this, we also developed a brochure for the town. What to do if you are designated as a red or a yellow or an orange? What is the possible pathway for you to do better now? Go ahead and do some, you know, rectification to your property to move to a better class. So these are some of the recommendations that we have done for these towns to make sure that they have a pathway, plus what to do during the storm and after and all that. These are going to be extremely necessary. So I would say the university capacity didn't have the opportunity to really make this one a kind of an activity to be done for all these towns. These are needed for all the towns around the country. Some towns have the resources, cities have the resources, they are developing it, some don't. So this is going to be key. If you're a civil engineer, especially focused in these areas, you have a lot more work coming your way. One of my recent grads got multiple job offers because there are a lot of projects, not enough people to actually get it done. So this is important area. I don't want to call it promising area because it's disaster. And, but it's growing. Flood is new. As we are developing more and more, it's going to become more of a problem. And it's going to become a dominant, factor. A lot of towns and cities, if you ask them, what is your number one issue, is actually the issue of flood. And I want to leave you with this. You have these now events pass through cities. So Hurricane Ida went through Birmingham, Alabama, killed 61, then went all the way up, Carolinas, and then in New Jersey, killed 21 people in New Jersey. We can't have these disasters to wreak havoc like this. And we have the knowledge, we have the capacity, we can do better. We are here to do better. The technology is being developed. And next thing is basically to be able to put it out in the market, in the use of the community. And hopefully you guys will be at the forefront of it to make this technology and technology like this commercialize and save lives and improve quality of life and save costs and help the cities to focus on areas that they really need, like housing and improvement of the, health and all that, rather than dealing with these natural disasters at this larger scale. So a lot of things that needs to be done. There's a lot to be discussed, which is not within my time, but if you have any questions, this is the right time. But thank you so much for having me.
I do start asking our virtual audience if they have questions. People from the virtual world, do you have questions for Professor Nazari? Any questions from the Zoom audience?
Okay, let's start from here then. It sounds like we don't hear many from there.
Okay, no question. No, there's one question. No, Matt. Okay, Matt. But again, just to tell you that in 15 minutes, there will be the Antico Pizza on the other room, 31, 33. So maybe if you don't have question, maybe you can still join. Okay, let's go here. So.
Who's asking?
No, that is a friend of mine from physics. So he has no questions. So it's
Rouzbeh, maybe is anybody from the students who want to ask a question? Yeah, go ahead. Yeah, okay.
Can you please be loud so they can also hear you from the Zoom?
Yeah. Thank you for the great seminar. My name is Fizi. I'm a PhD candidate in transportation resilience. And I have two questions. One short clarifying question. I want to ask, so you mentioned that in the evacuation route that's designated by the planning agency or whatever, they are flooded. So did you, when you did that modeling, this is a clarifying question, did you consider the construction, like the structural elevated?
Yes, so by the way, that work is already published. If you search for it, you have it. So one of the requirements for flood modeling is you have to have DEM and DSM, digital elevation model and digital surface model. So of course, if you're basic, so the base of most of flood model is something called bathtub model. Basically, you fill up a bathtub and how it goes based on if you have different objects in it. So elevation is the base that has to go there.
So what's the resolution of this DM?
So at the time that this one was the data, I didn't get into it. The data, we collected it. So this is drone and basically our own UAV stuff that we were able to fly it. We are down to around less than 5 inches of resolution. Whereas no slush and FEMA, you're talking about hundreds of feet. But the problem with those is for someone who does hydrology, having 100 feet that you don't know, that means an entire block, but that could be a pipe size of 100 feet taking water in and out, which basically makes rest of your calculation meaningless.
And then I'm interested in your other study about the damage on buildings.
Yes.
So you presented that from the equation about the flood damage.
Yes. That one is also published. That's in engineering structures, yes.
Yeah, so did you, I'm curious, like, did you calibrate the parameters or did you find them from?
So one of the things that we have done, that's a good question. So one of the things that we have done and we are doing now, but as a matter of fact, Mojongo is working on keep getting data sets. We are getting damage data from FEMA But at the time, because I was working for the government, I already had the damage data based on the specific blocks, because damage is mostly zip codes, but I had it based on building footprint, because this was a government funded project. I had access to that data through confidentiality. But also later I wanted to test the model, all right? And I had this. So after an event, we went around to see that, okay, so how this area that we modeled before, fared. So I had in an area, we predicted no damage, we had, multiple claims. Well, the thing is, FEMA comes around, I ask you how much damage you had, you say, you know what, I think that, $50,000, $60,000, they say, we'll give you a check for 20, you should, fine, sure, 20, keep it, that's good, right? So after that was done, they got that money and all that, students from the lab went around for calibration validation, started talking to people, and it's very different perspective when you talk to government officials and students. And the students went, okay, so how you doing? So you had this, major storm came by. Did you guys have damage? They're like, no, actually we fared very well. Nothing happened. And we were very lucky. So this system caught a lot of these false claims as well. So, initially, at the early stage, at a couple of insurance companies interested in buying the entire technology, I wasn't ready to sell at the time. But the whole, purpose of this one is also, if you would then have a sense of what you can expect, then you can direct your insurance adjusters and all that where to go. And in case if there is a false claim, then you could go back and negotiate and say, really, did you get all this damage or not, and all that. So that's a good question.
You got some compliment from the Zoom. Great presentation and very informative. No question for me. Good talk. So.
Thank you.
Sure.
Yeah, so I saw you present a plot between damage ratio and middle rise, high rise buildings. So I'm curious, how is the damage ratio being defined here?
So damage is an equation.
Yeah.
But also damage, as I said, all those, the chart that I showed with all the data, so it's a function of the fluid and structure system, fluid solid system. So the momentum of that one hitting the structure. So what are the keys? What are the possible damage? One is the type of structures in there, age of it, the material that was built. Also, first, floor elevation. The other thing is the presence of the basement. The other thing is, in a lot of places that flood is a common thing, they know that they have to move their key infrastructure to the attic. Where here in the United States, basement is where it goes. So actually, when water comes in, floods the basement, the most expensive ticket items are in the basement. Your HVAC system, your heating system, and all that gets damaged. And that's why one of the recommendations that we made was to actually move electric meters, gas meters, and so on, along with the infrastructure in the house, the HVAC facilities, to the attic. So damage is a component of those plus that equation that you saw. It's more complex than just one factor.
Okay, so in that plot, can I understand that damage ratio more like a damage probability?
This is an equation based. So resilience has probability in it, but damage specifically is to that equation.
So that is for measuring the damage that already happened.
Yes, the damage that is going to happen, yes.
Okay, I see.
Yeah.
And I have another question about the scour damage.
Yeah.
Like, how do you measure the scour damage, or where do you get the data to evaluate it?
So here's the thing, what do you think is going to cause a scour?
Storm surge, and there's a bridge.
Yeah, no, then go further. What else? Not necessarily just the water depth. It could be just 2 inches of water. What else is there? Velocity. So velocity component is used for that. So you have an area that not necessarily you get a high water, but you get a fast moving water that is washing around that system. And for that one, we also had data, and then the damage was specifically marked scour damage, the calibration validation process. So you have a different component over there.
Thank you.
Any other questions?
So Rouzbeh, we like that seminar a lot because it's not only the science part, it's also.
Can you speak louder, please?
Yeah, so I was talking to Rouzbeh. So I have 200 questions or so, but the impact that you were getting to, What was the result? I mean, it's a new study, so it's just been published, right? So you're trying to convince people, but is there anything that the officials did to kind
Oh,
of?
yeah. So there are a lot of different things that the government officials did, and it's not within this, conversation, but. So there is something called CRS, the Community Rating System. So a lot of coastal towns, all the towns that they are paying flood insurance premiums, if they get into that FEMA CRS program, it has 10 classes. Basically goes from, 1 to 9. You first get in, you become class 9, and every class that you go up, you improve by 5%. Your insurance drops by 5%. So you have some of these communities that they are in CRS class 4 and 5 that get around 25 to 30% reduction in their insurance premiums, not only for the city, properties, for everyone in the town. So it's a major brag point for the mayors that I came in, we got into CRS, and now we are class 5 or 4. To go from class 5 and 4 to class 3 and to a better class, they have to do also a watershed management plan. Watershed management plan is costly. Some of these companies charge around $200,000, $300,000, $400,000. One of the things that we have done is because we have developed so much data for these towns, we gave him all that data. It helped them to get on CRS and jump to the class 5. That means significant saving. You're talking about 25% saving for a town. That could be around $15 million of a saving. So that's just one of them. The other thing is, if they're getting capital improvement, money coming in, they have to apply for it. The requirement for that is to write a proposal. Proposal writing, as you know, needs data. They don't have any of the maps, projections, analysis, and the data. For them, they were able to get a lot of funding from the government because they had these data sets. And after that, as I said, I had many more towns that they wanted us to do this. But again, for us, we have to get the funding to do these kind of things.
Yeah.
And that's a whole process. But as a company, this could be a service to be provided.
So the other question I had was the regionalization thing, where you beat the heck out of this system and you collect so much data, etc. So you got a lot of information. But you said that you think you have a sense that you can regionalize this. That is it possible to do this here and then move a little bit to the north in whatever?
That's a great question that you asked, and it basically, because you're in this field and you know it, because the watershed boundaries, what Dr. Georgia Carcas is talking about, watershed boundaries doesn't fall within your county or zip code. That's the watershed boundaries. So you're doing a study, let's say for Atlanta, but you have to go significantly beyond that to basically capture that entire watershed. So even though you're going to do a small town, if it's part of a larger watershed, what do you have to do? That's why if you're doing this one on a company base, you have to count the size of the watershed. And the issue that I was pushing at a time in the Northeast is to stop working within the limits of your towns and your counties. You have to have a regional approach. You have to become part of this watershed and start sharing resources. So as you said, even if you're doing a small town, sometimes you have to do larger parts. Even though I've done the study for some of those towns, I had to do entire state and the part of the Eastern Seaboard to make sure that I have all these nuances involved. Yes, so it takes a lot more. But we were lucky, we were part of the university. We have access to, as I said, a smart but very affordable labor, AKA graduate students.
So my last question is this, that I think that the last part you talked about potentially using this in real time when the question was about which the road is on. So is there a plan with the startup you're talking about to create, you said the mobile app?
Yes.
Okay. Now, is there a possibility for that? Now it's very common, what I'm going to ask to tell you, to actually collect information to outsource information, from the people who are there and saying, okay, they're trying to get back and give you data.
Oh, absolutely. That's another, great point. So one of the other things about this is that you have the users basically uploading some of the images. But in addition to that, there's another part that I didn't talk about it. During that event, Sandy, 48,000 cars were under water, so you got flooded. Just think about the massive cost of that. So as a part of this app, because it has the street level data, we'll give you a warning if you're using it that your car is in the zone that is going to be flooded. Now is the time to move it, and these are the proposed locations. Whereas over there, you get basically information from the users that yes, the street is flooded, and you're constantly, doing some of that image analysis. But if you talk about at the start of the company, part of it, my focus has been, and I'm trying to do, and I'm hoping that, with, some more traction that we get, is to push that first product out. And with that one, create that buzz and the recognition to push out. I have around 9 other products that could be pushed out of it.
And the last question that I was thinking to ask is you are from another country.
Yeah.
Me too. Most of us here are.
Yeah.
Here in the United States, perhaps we have the technology and with a little bit of push and shove, you can put it in place. You think what happens out there in the developing countries, in your country, in Africa, for example?
Oh, yeah.
It's going to be, so the question is not, I know the technology is not there, but is it with the satellite system and with the mobile apps, is there something we can leapfrog into for these areas and something that is useful for them too, not just for these countries that are.
Absolutely, and then the problem is not just those underdeveloped countries. You know that a couple of years ago, there was a flood in Germany that killed over 200 people, and this is Germany.
Yeah.
And then when you go to India and Pakistan and Iran, you're talking about 2,000, 3,000, 5,000 people dying, just being washed away. The problem is these are data intensive. So I can tell you the government of Philippines have been trying to get me to go and do a project over there for the past 5-6 years, because there's 7,000 islands. So everything here is just significantly jacked up. So, but we have so much issues here, but I'm hoping that once we develop a system here, we could actually take this technology then on the road. This becomes a global model. As you said, with the satellite data, with combination of all these high resolutions that we have, we definitely can develop a flood model. Maybe it's not as sophisticated as it is because we don't have the infrastructure, all these other things on that system, but we can have something acceptable that have a timely warning system and avoid those major catastrophes. Like instead of like having 2,000 people die, actually minimize that. That's the number one thing.
So that would be great.
I have 2 questions.
Sure.
One question is, what struck me on this plot
Yeah.
is that the 3 curves, you have three states, the curve are very sensitive, you slightly change your resilient index, and you can go from good to poor. So, I see that is highly sensitive. And that's maybe, I don't know why it should be like,
Yeah,
I would expect, for example, the damage index, is less sensitive, so there is more.
Restoration curve is less, with it.
But why vertical, you just change the residual index by 0.1 and you
Yes.
go from good to poor. Is that why?
So, the heart of it is, if you have a major event, a category 4, 5, that is large enough, that is not going to recognize that if you come on your luck, then everyone is damaged. But when you're trying to restore, then your financial prosperities, your income and the rest of things will come into play and then play that role. Because as a result of that, if you go here, you see that a lot of these, even coastal communities, that they're highly vulnerable. But if
you
you
see
go
here,
there,
you have nearby buildings, they are red and green.
exactly.
Why?
So some of them actually build better, they have better infrastructure. So I give you a sense. In this area, DEP had some funding from flood. They were going from FEMA. They were trying to build the flood wall. Community was saying, what are you talking about? We have a beach view and we want to protect it. So our model showed that once that wall went up, which is right around down here, all these properties are now green and protected. And also the point for this one to make this one commercial that you can buy it is some of these properties, they're built better. They have been raised. They have done work to it. Now they are not at the same level of risk. So then they should actually become more valuable. So pricing shouldn't be based on, oh, okay, I like this. It should be representative of some of the fundamentals too. So if someone spent all that money, raised the structure, secured it and all that, right now it doesn't show. But with this, it will show. So one of the things that, I told the mayor that, we were never going to put this map out there, but they were going to bring the residents and tell them about it. But a lot of the homeowners are elevating their properties. They're working on, stormwater management systems to improve their property. And I told them that if they basically filed their LOMA, basically their certificate of the elevation, we will put it back in the model and rerun it and tell you that if they have fared better. So that's one of those things. If you do better and now you submit your results, we can show you that, you know what, this actually went from, red to yellow now.
I think here if you add an extra axis, an extra dimension, and you do that plot 3D by adding an extra parameter that characterize the housing, then basically, this, because what you did now is like you have a 3D surface, and you basically squish it onto D.
Yeah.
You basically are able to pull it
Take
out.
the third dimension.
That
Sure.
basically, is gonna. The other question is, I would like to, here there is a lot of mathematical modeling and simulations. Yes, so you're doing all. So from a statistical point of view, so here you're dealing with physical processes that are non-stationary, transient, then, especially inhomogeneous, and so you name it, you have it. So what are the mathematical what are the mathematical tools that we're using? So stochastical modeling, how you do the stochastical modeling. So because you cannot do ergodicity, so you have to do a lot of ensemble averages, I guess. So, what would be also a dynamical system perspective of, this approach, and how would you use machine learning, which
That's a great question. That's a great question.
So how would machine learning, for example, here?
So one of the reasons that, as you see, AI hasn't been successful, so pizza is here, so I'm gonna stop right away. So,
Pizza is here.
yeah,
It's
so,
going around.
one of the reasons that machine learning hasn't been successful in this. Because for a lot of the startups, now obviously this is an area that is very interesting. The reason that those companies haven't been successful is this is not, as you correctly said, just a statistical problem. Because you have physical parameters that they involve. There's civil engineering stuff that has to be involved in here. Unless you have civil engineers developing those models, this is not gonna work. Because the underlying momentum, the forces, the fluid and solid, interactions, and all that, they are equation, they are basically that direct relationship that's been developed. So that's why machine learning and AI haven't been successful in this area because of the fundamental issues. Unless, the fact that what Mojongo and Ali Reza, they're gonna work on the postdoc and the PhD student that they're actually on the Zoom call right now, is basically now bring those fundamental equations into it as a part of that machine learning to do the training, and then let the machine learning take over, now to have a educated way of doing that.
At the beginning, the last things, at the beginning, you show a video of a building deformations.
Yes.
I want to ask you, because I saw some deformation on some, I was trying to understand why, the deformation, I can understand, the diagonal traction there because it's normal, but then looking at the door, in the middle of the door, there is that compression.
So this is a plasticity model.
It's a plasticity model.
Yes, this is a plasticity model. This is the paper in engineering structure, has all these components. And it actually is a very long paper. It's actually 15 pages. It goes through all this.
Basically, the door is very tall, and so
Yes.
there is, that's makes the structure less rigid.
Exactly.
So when I assume, you have this large moment of deflection.
And as such, you will see some of the real scenarios that the crack is actually happening.
No, the diagonal is perfect because those are the line of, the principal direction of traction. So
Exactly.
that's it's fine. So I was trying to understand even the one on the top there. So these are all plasticity models. Okay.
Yeah.
One last question we take.
So,
Two last questions. Two last questions.
okay.
Whatever you say, yeah.
Yeah, but the pizza is very hot. No, let's
Okay.
get the pizza because we don't want them to.
If you want, we can talk, as we're having the pizza. Go ahead.
So my question is that for the model that you built to predict flood damage, how would you measure, evaluate the model? Like scour damage model, how would you evaluate that?
So as I said, so the only way that you can do the evaluation is look at some of the real scenarios. So that's why we're getting these real damage data from government agencies to basically do our simulation and then do simulation versus observed. So that's our calibration validation process.
Yeah,
That has been the case, the whole thing. Yeah.
Is there enough data that is available?
Oh, yeah,
Scour?
data is always a problem, yeah, it's hard. As I said, we're still, even now, we're begging FEMA to give us more data.
Okay, yeah, I see.
Data is, yeah.
What kind of diameter that you use?
So in this case, for that one, FVComp, specifically FVComp that we used.
I mean, there is like a slushy or, I mean, the boundary condition, because it sounds like you use the slush, but the,
No, a slush is a NOAA model.
yeah, that is reference or just.
Yeah. Yeah, we didn't use a slush, you know, I have a whole conversation about slush.
Your model including the drainage system and the inland stormwater system?
No, this is not a full basin, yes.
Because as I remember, in case of hurricane Sandy, some inland subway station of NIC was submerged, so people
Yes.
could use the broccoli ability to cross the river and the tide. And in that case, the urban model, without the urban model, is hard to.
It's hard to do
the-
But here's the thing, even urban drainage system is only functional within the first hour of a storm. After the second hour, all of that is clogged. So you can ignore the first hour of the storm in general. If you're working on an urban model, there's a drainage system, you can ignore it after the first hour because generally it gets clogged. The data that I showed during Sandy, what happened, that was an observed, that's a FEMA modeling task force motive. That was the data that FEMA put out.
So he's asking this question because he's working, his PhD is doing a detailed model, and Dr. Lu and I are helping.
Oh, I would love to
Yeah.
talk to
So
you more
detailed
about
model about the whole system, using the same kind of idea, the footprint of all buildings and how the floods are going to happen from the waters and everything, all the way down. And it's not about hurricanes, what he does, but so I'm saying, from that experience that we have here, he's been working on that, he's doing some terrific work. This AI thing is going to be different for the causes that actually create the flooding from place to place and whatever. So I wonder what uncertainty this thing would actually create. If you take the stuff you have in a particular region, do this AI thing and then apply it somewhere else. It would be interesting to see what kind of an uncertainty.
Oh, like that data, that model has to be retrained for every